Welcome back, ladies and gentlemen. Today we're going to be continuing with two-dimensional velocity, but now we're going to talk a little bit less about the math and a little bit more about what it all looks like. Yep, it's all going to be about perception. Now, if you've done your homework, as it were, and watched the video that I posted a link to, it's an old one for those who haven't yet looked at it. I do recommend it. Only the first 15 minutes or so, then it gets a little too detailed for our purposes. But if you've taken a look at that video, you will discover that they spend some time talking about and demonstrating what's effectively a series of magic tricks. And what you discover is that even though the math to calculate someone swimming across a river is fairly straightforward, what it means and what it looks like, what it appears, is not. So as the notes say, all motion is relative. You've seen this when you stand in an elevator or try to gauge the movement of something without a reference point. The problem is nothing is fully stationary, so we have no single fixed reference point. The Earth appears stationary to us because we stand on it, and yet we know that day becomes night, so the Earth must be moving. In point of fact, it is moving almost 1,600 kilometers a second, and yet we don't feel it. To make some sense of this topsy-turvy world, we need some new rules and some new notation. So the notation is the first part of this. The notation will look something like this. And what this is telling you is, of course, velocity. It's got a V in there. This would be, say, a car. And this first letter is the thing we look at. And the second letter, which in this case could be, say, the Earth, is where we look from. So in this particular instance, we could say that this notation is telling us the velocity of a car with respect to the Earth, or as seen from the Earth, something like that. So what this type of notation is trying to say is, what do I see if I'm standing on the Earth looking at the car? Okay, now in the video we would have seen a variety of unusual and quirky situations, right? Like when they were sitting on the cart together and they were passing the puck back and forth. And what we notice, of course, and what they try to show us, is that as the puck is going this way or this way, we will see something different in terms of its speed, depending on if we were standing on the cart with them or on the ground. And this is kind of the thing. Again, if we think about the Earth, right? Right now we're sitting on the Earth. I'm assuming that you guys trust that I'm not filming this in space. Right now I'm sitting on the Earth, and this is moving at 1,600 kilometers a second, and yet I'm not zipping around all over the place. So what's happening? Well, if we were up in the International Space Station looking down, we would see the Earth zip by really fast, because we're no longer standing on the Earth. Similar, if I'm standing on the Earth and I'm looking at a car drive by, the car will go by really fast, especially if it's on the highway, or if you're speeding, don't speed. But if I'm in the car, I can look around at the different parts of the car and everything seems to be just sitting there, right? I mean, if I look out the window, I can tell I'm going fast, but by itself, I can't really tell. So there are a series of rules. I'm trying to remember here. We got six rules around relative motion for us to understand this, okay? So we're going to work our way through it, and we're going to need this notation, right? This notation is going to be helpful, right? So remember, the first term is what I'm looking at. The second term is where I'm standing when I do the looking, right? So right now, for example, this is telling me that I'm standing on the Earth and I'm looking at a car. If I flip these two, right, if I put the E up above, and I put the C down here. So if I switch it like this, if I make this E and this C, then now I'm in the car looking out at the ground. That's what that would be. Okay? But we'll see this as we go through the different rules. Okay, so rule number one of relative motion. And remember, No matter how weird this is going to get, no matter how weird the video was, no matter how weird anything is, the math is always the same. It's always Pythagoras. So first rule, if you are moving with something, it will seem stationary. So rule number one, the velocity of the Earth with respect to the Earth is 0. The velocity of a car with respect to the car is 0. That's it. If you move with something, it does not appear to move. I'm on the Earth, it is moving 1,600 kilometers a second. I don't feel it because I am also moving 1,600 kilometers a second. If I wasn't, then of course the Earth would go whoa, and I'd be stuck in the middle of space going, well, this is bad. So that's the first rule. If you are moving with something, you don't feel it at all. Well, that's pretty straightforward so far. Rule 2. If you are not moving with something, its motion is found with vector addition. So the velocity of the car with respect to the Earth is going to be equal to all of, is going to be found, maybe not equal, we'll say found. Now we know two different types of vector addition. We know one-dimensional and we know two-dimensional. We've already done some two-dimensional vector addition with velocities in the previous set of notes. But just to remind us what the cart and the what we saw on the video, if you're on a cart and the two professors were sitting on the cart and they were passing that puck back and forth, like so. There were two possibilities. Here, let's do this in another color. Possibility number one goes this way, and the car goes this way. Okay, so this is going to be the velocity of the car with respect to the Earth, and this is going to be the velocity of the puck with respect to the car. So the velocity of the puck with respect to the Earth, we're going to find it with vector addition. Puck, car, plus car, Earth. Ta-da! It's added. Why? The two vectors point in the same direction. Now, if one of the vectors was pointing the other direction, let's say this way, then I don't add them anymore. Now what I do is I subtract them. So I end up with something that looks more like this. That one's negative, plus the velocity of the car with respect to the Earth. So they will subtract because, of course, one's going backwards, one's going forwards. And again, we saw that in the video. Hopefully, this is all making pretty solid sense. Now, you'll notice I did a bunch of weird notation with the algebra there. That leads into point 3. Velocities are generally listed in a nested order. So what that means is that, as we saw here, the velocity of the puck was told with respect to the car. So like if we had a little person sitting here watching the puck go back and forth like we did in the video, we would see this velocity. And then or this one, depending on if it's forward or backward. Then the car was measured when somebody was standing on the ground. Now this isn't the only way that we can do this, but it's a pretty standard way. So the example in the notes here says that a mouse runs on a car, rolling on a boat, sailing down a river, flowing towards the sea. Whew! So we've got a mouse running on a boat, oh, I already got it wrong. There's a mouse running on a car that's rolling on a boat. The OAT, comma, sailing across a river, comma, flowing to the sea. We got a nested series of things. So we're going to put ourselves a nice little river. And we've got ourselves, water. And the river's going this way, the velocity of the river with respect to the Earth. Why? Because the Earth is the next layer down from the river. What is above that? We're going to have a boat. We'll do the boat in red. So here's our boat, our incredibly fancy boat. And we're going to say that the boat is moving, sure, let's go this way. This is going to be the velocity of the boat with respect to the river, because the boat is in the river. Then we're going to put a car on the boat. And we're going to say the car is going this way, and it's going to be the velocity of the car with respect to the boat, because the car is on the boat. And then finally, we'll put ourselves a little mouse on top of that thing. I'm going to put a mouse, let's see, we're going to do a mouse right here. There's his little nose, there's his tail, and we're going to say the mouse is going this way, and that's going to be the velocity of the mouse with respect to the car. So you'll see that each layer here is built on the other ones underneath it. Now this is important because it does set up for number 4. To find the velocity of any one aspect, we can sort of employ a fake algebra. What do I mean by that? What's the velocity of the mouse with respect to the Earth? Right? If I'm standing here on the shore looking at this weird rolling, running, sailing, floating type of thing, what do I see? Well, here's how you set it up. The velocity of the mouse with respect to the car plus, it's vector addition, the velocity of the car with respect to the boat plus the velocity of the boat with respect to the river plus the velocity of the river with respect to the Earth. Now look closely at the terms. Do you notice something? There's a car in both of these. There's a boat in both of these. There's a river in both of these. What am I left with is mouse and Earth. And that is what the question was asking me for. Oh, well that's not so bad, right? Like, okay, fine. If I want to find the velocity of the mouse with respect to the Earth, I just cancel things out as I go. What happens if we want to do a different one? All right, fine. Let's do the velocity of the mouse with respect to the river. Okay, it's a little different. How are we going to find that? Well, we want mouse, so I'm going to put mouse there, and the only one I know is a mouse to the car. Okay, so that's the first one. I got to get rid of this C, right? I don't want that. I want an R at the bottom. So I'm going to go, where do I see a C? I look at my diagram. I got a C with respect to a B. Okay, so I'm going to put a B there. Then I'm going to do a little further. I want to get rid of this B, so I'm going to do B with respect to the R. Hey, look at that. The C's cancel, the B's cancel, and we're left with M and R. That'll give us our answer. So we can put this all together pretty straightforward, right? Like, it just is addition, right? That's what we see here in point 2. It's just addition. But in order to know how many things to add, we just simply check, what do we need on the top? Well, the top, and what do we need on the bottom? How many do I add? I add 1 for every step until I get my letter for the top and my letter for the bottom. And that's it. That's all we have to do. Well, I got 2 more points here. What does it say? The path of the motion will seem different if you are stationary or in motion yourself. What does that mean? Let's look back at our river again. We're going to need a little bit of space. Which one do I want to erase? See, normally I prefer if I've got more of a board to work with, but we can't have it all. We'll go back over here. If I am in the river, all right, we're going to go back to the river. if I am in the river, we're going to have the river pushing somebody up like this, and we're going to have the person do the simple thing, and they're just going to try to swim right across. Okay? So this is going to be the velocity of the swimmer with respect to the river, and this over here will be the velocity of the river with respect to the earth. And then, of course, there is this green line here. What's that going to be? Well, let's take a look at equation 4. If I add these two together using vector addition, I'm going to get the velocity of the swimmer with respect to the river, the velocity of the river with respect to the earth. I'm going to do some vector addition to add them together, and what do I get? Velocity of the swimmer. R's cancel with respect to the earth. So that's what this is. Swimmer with respect to the earth. So if I was standing here on the shore watching the person in the river as they swim, I will see them swim at an angle across the river. And usually this throws people because they're like, wait. Here I see them swim at an angle. But what happens if I'm here in the water with them? Do I still see them swim at an angle? No, you don't. If you're in the water, you'll see them swim straight across. Why? Think about it like this. You and your friend are sitting there on the shore of the river, and your friend gets in the river. Let's see, how am I going to do this so you guys can see? Here we go. We'll do it like this. Your friend gets in the river. Huh. They then swim down. Huh. And then the river pushes them over. There we go. So you, just standing here, are now seeing your friend at an angle, right? They're some distance away that way. The next second they swim down, and the river pushes them over. The next second they swim down, and the river pushes them over. So clearly there is an angle from here to there, right? I could draw a line on the board from my blue pen to my red pen down here. But now let's think about what happens if you both get in the river. So you start in the same place, you both get in the river, boom. Your friend swims down. Then the river pushes him and you like so. Then he swims down again, and you both get pushed like so. Then he swims again, and you both get pushed like so. You have also moved. You are not over here like last time. You're over here. For you, your friend doesn't look like he swam at an angle. It looks like he swam straight across. So remember, if you are moving with something, it doesn't look like it's moving at all. So the velocity of the swimmer with respect to the river is just this red number. The green one only comes into play if you are standing outside of the river. All of these different rules, they lace on top of each other in order to make sense. The last piece of this puzzle, right, this one here was number 5. The last piece of this puzzle, we'll say right here is number 6, is that the inverse, so the velocity of the swimmer with respect to the earth, for example, let's pretend that one was plus 10 meters per second. Well, that means that the velocity of the earth with respect to the swimmer will be negative 10 meters per second. The rule is you inverse the symbols, you flip the symbols, you flip the sign. Now why? Well, again, think about it. You're in your car, right? You're in your car, and the car is driving along. Right? So you're sitting here in the car is driving along. To anyone standing on the ground looking at you, your car zips by, right? You just, there it goes. But you don't see that. You don't see your car zipping by. What you see is them going backwards in the window, right? If you glance out the window, you'll be like, oh, hey, there's my friend. Oh, there he's gone. The friend looks like they're going backwards. How do we show backwards? Negative. So what does all this mean when we put it all together? When you're in the river, you don't see any motion from the river. When you're standing on the earth, you don't feel the motion of the earth. You only see this vector here, the swimmer with respect to the river, because you're in the river. If you're on the earth, you would see these two combined. depending on where you are, right? If you're busy looking at your friend swim, you'll see this. Well, your friend will see the opposite. He'll see a negative vector going the other way because it looks like you're like getting further and further behind him, right? I said that I'd be like this in my example. Well, for you, it looks like your friend has gone like this away from you. Well, from your friend, it looks like you've gone backwards away from him. We've also seen how to do this in terms of the addition. It's pretty straightforward, really. Lastly, we discovered that if the object is moving at the same speed as you don't notice it. All of these things come together for the addition. And when it comes to vector addition, remember, if it is one-dimensional, you just add it as is. If it's two-dimensional, you use Pythagoras. So in this little example here that I drew, I've got vectors going all which ways, right? I've got vectors going left and right, and I've also got at least one vector going up. Adding this one, and this one is all one-dimensional. So this, and this, I just add the numbers as is. When I have to, however, take all of these added up and add it to this one, then I have to do some Pythagoras because now it's two-dimensional. But that's just the rules of vector addition. If it's 1D, you just add the numbers. If it's 2D, you Pythagoras that thing. So at this point, I usually turn you guys loose with a little bit of an exercise. So I'm going to put it on the board. Then I'd like you guys to pause the video and try doing the exercise. I will then show you step by step how to solve it. This little exercise will use all of these rules that we have just covered. The situation is as follows. We have an airplane in the sky. A little observer in the airplane. The airplane is moving with the velocity of the plane with respect to the Earth. Is that what I went with? Of 500 meters per second. Then, on the ground, we have a car. And the car is going this way with the velocity of the car with respect to the Earth. And again, we're going to put a little observer in the window. And this one I'm going to say is moving at, I think I chose 30. But the person in the car, kind of a jerk, and they decided to throw, let's go with red. They decided to throw a piece of trash, a huge piece of trash apparently, backwards out the window. And the velocity of this trash is -1 meters per second. Now remember, we tend to nest, so that's with respect to the car. So this velocity here, this -1, is being measured by this guy in the car. Okay? So this is our situation. And what I want you to do is I want you to figure out every possible perspective in this puzzle. What velocities can you see from every different position in the entire thing? What do I mean by that? Well, let's work it out. There's the velocity of the plane with respect to the Earth. There's also the velocity of the plane with respect to the car, the velocity of the plane with respect to the trash, and the velocity of the plane with respect to, well, the plane, I guess. There is the velocity of the car with respect to the Earth, the velocity of the car with respect to the car, the velocity of the car with respect to the trash, the velocity of the car with respect to the plane. I think you're starting to see the pattern here. The velocity of the trash with respect to the Earth, the velocity of the trash with respect to the car, the velocity of the trash with respect to the trash, the velocity of the trash with respect to the plane. And the last set, almost done. Velocity of the Earth with respect to the Earth, the velocity of the Earth with respect to the car, the velocity of the Earth with respect to the trash, and the velocity of the trash with respect to the plane. Those are all of the possible relationships that we could have in this situation. And that looks like a lot, and it looks super complicated. It's not. Break it down, okay? So I'm going to pause it here, or at least I would like you to pause it, and try this on your own. See what you can do. I'll give it a few seconds here. for you to hopefully pause and try it. I do recommend it. Then I will show you the answers. All right. First things first. We already know some, so let's fill those in. The velocity of the car with respect to the Earth we know is going to be 30, positive 30. We can write that a little better. The velocity of the trash with respect to the car, we also know that's minus 1. And the velocity of the plane with respect to the Earth is plus 500. So those three we have from the beginning. Now, the last rule of our relative motion rules, Rule 6, says that if you flip the letters, you just flip the signs. So if this is plus 500, because it's the plane with respect to the Earth, then the Earth with respect to the plane, which is what I totally wrote over here, I don't know what you're saying. The Earth with respect to the plane will be negative 500. Because when you're sitting in the plane, you will watch the ground go backwards away from you. So the trash with respect to the car is negative 1, so then the car with respect to the trash is positive 1. What that means is that you see when you're standing, if you were imagining yourself standing on the trash, you would watch the car slowly get away from you one step at a time. The car with respect to the Earth means that the Earth to the car is negative 30. Again, it looks like it's going backwards. All right, so that one was pretty easy. There's one that's even easier. Really, I don't know why I didn't start with this one. Anything with respect to itself is 0. That is 0. This is 0. Trash with respect to the trash is 0. Plane with respect to the plane is 0. And this is a pretty good thing, right? Like, if I'm in a car and I reach for my wonderful beaker of water in the cup holder, yeah, the water in the cup holder is moving, like, in this case, almost 100 kilometers an hour, more than 100 kilometers an hour. And yet I don't have any problem getting it. Why? Because I'm also moving 100 kilometers an hour. If I was standing on the, edge of the road and I wanted to reach into the car in order to grab the cup and pull it out, well, that's a lot harder because now, of course, I'm not moving compared to the car. So I have to be able to, basically be the Flash. And that's not happening. Okay, what else do we need? Well, those are all the obvious ones. At this point, we now have to start doing some math in order to figure things out. So, well, let's see. Let's do, really, any of them will work, but let's just choose one. Let's do the velocity of the trash with respect to the Earth. Sure, it's right here. It's the first one. Velocity of the trash with respect to the Earth. So in order to do this, I need the E on the bottom and the T on the top. So that means that there's going to be a T over something plus something over T. Oops, not T, E. Right? And these two question marks have to be the same so they cancel with that weird fake algebra thing that we're doing here. So, well, I only know trash and car, right, off the top of my head, so I'm just going to put car here. And that means that I need car and Earth there in order to make this whole thing cancel. Well, I know those numbers. The trash with respect to the car is minus 1, and the car with respect to the Earth is plus 30. Now, they're both in the same dimension, right? This is one-dimensional. One's going forward, one's going backward. So I don't need to do any Pythagoras. I just need to add those numbers. And what do I get? Plus 29. So this one here is going to be plus 29. So what that means is that, again, think about it. From standing on the Earth, you watch the car go, and the car is going 30 meters per second to the right. The trash being thrown out the window is going 1 meter per second backward, but that means that it's still going forward mostly. It's just slightly slower than the car. So it'll be going 29 meters per second forward in total. Now, once we have this one, its corresponding one is super easy, negative 29. Right? So that one just automatically fills itself in. Hey, look, we've already finished this entire row. Well, that's pretty convenient. Okay, let's do another one. As we fill things in, other things become easier. So can we do T over P? That's the last one of that row. That'll finish it off. So let's see, the velocity of the trash with respect to the plane. Okay, so in order to do this, we're going to need a trash on top with a question mark, and then we're going to need a question mark on top, and then we need plane on the bottom. I need a single symbol, right? It has to be the same for both of these. So if I look at the numbers that I have, what I could do is put E for both of them, right? We just figured out this one, and we already know this one because it's the inverse of the one that we had to start with. So we put all that together, and what are we going to get? Well, this is T over E, so we know that one is plus 29. And E over P, we know is minus 500. And we're just going to add them. So I'm going to take my trusty calculator, 500. And I'm going to get negative 471. Now again, does that make sense? When you're standing on the plane looking down at that piece of trash, the trash is going backwards. And it is going backwards because you are, of course, going super fast forward. But compared to the ground itself, the trash isn't going backwards as fast because the trash is moving forward a little bit with the 29. So that's why it is still going backwards, but not as much. I mean, it's still a lot because an airplane is fast, but it's not as much. Now, once again, we know T over P, which means we know P over T. This one here is going to be plus 471. Plus 471 means that, well, first of all, that makes sense, right? If you're standing on the trash and you're looking up at the airplane, then you've got to maybe make some choices about where you're standing. But what you see is the airplane is moving forward, but not as fast as if you were on the ground looking at the airplane, because when you're on the ground, you're not moving at all. Okay, well, if you look at that, guys, we've only actually got 2 left, and once we solve one of them, we get the other. Even though there was so many numbers here, right, there was 16 that we had to solve, we've only had to do 2 calculations so far. The rest of these are just flipping things or making things zero. All right, well, let's do the last one here. Let's do plane over car, sure. So it's going to be plane here and car at the bottom. So if this is plane over car, and this is something over car, sorry, plane over something and something over car, and they need to be the same thing. Well, we've been consistently using the Earth for this, so let's do it again. The plane with respect to the Earth, we know that's going to be plus 500. The Earth with respect to the car, we find on our little list, negative 30. So, well, that one's a pretty easy one. That's going to be positive 470. Which means this one is going to be, this one is going to be negative 470. And there you have it. We filled the whole thing in. Now you'll notice I used colors to do that on purpose. The black numbers were the ones that we were given for the start of the question. The green numbers were the ones that we knew were zero automatically. The blue numbers were the ones we calculated, and the red numbers were the ones we filled in without having to do anything at all except to invert the sign. This, in some ways, represents relative motion pretty well. It looks complicated. It looks like a lot of work, but it's not. The math we're doing is just vector addition. If it's in one dimension, like these, we just add the numbers as is. If it's in 2 dimension, we get all Pythagoras on it, but again, we know how to do that. What we're seeing in terms of the setup here is that a lot of this is just sort of naturally coming out of the basic rules that we have to work with. Yes, we have to learn those rules. Yes, we have to understand the notation. Yes, there is still some math, but despite how weird and wacky this stuff looks like, it's not actually that hard. I mean, Chase problems were harder than this. Come on, right? So I think you're going to find, as you guys are working through the next several pages of relative motion, so long as you keep the basics in mind, this is going to be pretty straightforward. So that's the last bit of notes for relative motion. At this point, there's just going to be a lot of practice. So make sure you guys get that practice in, and I will talk to you next time.